We ended up talking about acid-base neutralization reactions at our last class meeting. And tonight we're going to talk about acid-base titrations. This is just a technique that makes use of an acid-base neutralization reaction. So titration does not have to involve an acid and a base. But what happens in a titration is that we have a substance in a solution with a known concentration, and we react it with another substance where we don't know the concentration. The goal of it is to find the unknown concentration. We add one solution to the other until the reactants are in their stoichiometric ratio, and that's called the equivalence point. So in an acid-base titration, typically you're adding base to the acid, like sodium hydroxide to hydrochloric acid, and you're going to keep adding until you get just the right amount. Of course, how do you know when that is? That's kind of the tricky part. When we're done, we can use the volume of the known solution and its concentration to calculate the unknown concentration. So for acid-base titrations, the solutions are clear and colorless, and so you can't really see anything happening, but we can pinpoint where that equivalence point is by adding an indicator. An indicator is a substance that changes color dramatically in response to different pHs. So at the equivalence point in an acid-base titration, we have the number of moles of hydrogen added equal to the number of moles of hydroxide added. So this is an experimental technique. Solving the problem is just a solution stoichiometry problem. So here are pictures and drawings. So typically we'll have something like this sodium hydroxide in the burette. We've used burettes. Now, when we start doing titrations, that's when we really get serious about using burettes. The burette is great because you can measure out a certain amount of liquid and then find out what the volume was, as opposed to like a graduated cylinder where you kind of have to say, well, I'm going to do this much. And then you pour it out and you find out that was too much or something. So we've got the sodium hydroxide in here, and then we have our acid down here. As we add sodium hydroxide, the hydroxide from that base reacts with the hydrogen ions from the acid and neutralizes them. When we get to the equivalence point where we have an equal number of hydroxide and hydrogen ions, the pH will change, and that causes the indicator to change. Very common indicator we use is called phenolphthalein, which is quite a mouthful, and I won't require you to spell that. It's going to change color from colorless to pink. Now, we'll learn that that pink is a little too intense, but it's good for illustration purposes. As it gets closer, you'll start to see a little bit of color where the drop of sodium hydroxide comes in, because it hasn't mixed yet. And in this local region here, there's more hydroxide, and so it turns pink. But then when you mix it, by swirling it, it goes away. So, have you guys done titrations before? Okay, mixed. That's what I expect. So let's do this calculation related to a titration. So a titration of 20 ml sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of a 0.158 molar KOH solution to reach the equivalence point. What is the concentration of the unknown H2SO4 solution? The thing you really, really should do when you're doing a calculation for a titration is write the chemical equation. Okay, we've learned how to do that. Write the balanced chemical equation, And remind yourself, this is a stoichiometry problem. And don't be tempted to take any shortcuts. It's just a stoichiometry problem. Having issues with my device here. Okay, I think it's going to cooperate. So we're told that H2SO4 is reacting with sodium hydroxide. So that's an acid and a base. What's one of the products going to be from the H plus and the OH minus reacting? Okay, we can't remember. That's fine. So the H2SO4 is going to give us hydrogen ions and sulfate ions. And the sodium hydroxide is going to give us sodium ions and hydroxide ions. And how do we predict the products? We switch partners, right? So we're going to put sulfate with sodium and hydrogen with hydroxide. So over here we're going to have hydrogen with hydroxide. And when we put those together, it looks funny, like HOH, huh? And then we remind ourselves, no, that's water, that's H2O. And the other one, sodium sulfate, we have to consider the charges. So it's not NaSO4, it's Na2SO4. Everybody okay with that? Is this equation balanced? No, it's not. What jumps out at you that's obviously not balanced? The sodiums, right? Because there's one over here and there's two over there. So if we put a 2 over here, that'll fix the sodiums. There's one sulfate and one sulfate. So let's count up the hydrogens. Over here I have 2 hydrogens and 2 more hydrogens there. Over here I only have 2. So I need to put a 2 in front of the water to give me 4 hydrogens. The oxygens can be a little confusing because they're all over the place. Let's just look at all of them together. There's 4 here and 2 there. That's a total of 6. There's 2 here and 4 there, a total of 6. So that's our balanced chemical equation. Now I can take the numbers from the problem and write those under the formulas in the equation. So it tells me that there's 20.0 milliliters of sulfuric acid solution. We don't know what the concentration is. They tell me there's 22.87 milliliters of the sodium hydroxide, and its concentration is 0.158 moles per liter. What are we trying to find? Concentration of the H2SO4. So that's right here, question mark, moles per liters. So we know the volume, right, of this solution. What else do we need in order to calculate the molarity? Well, we need to know how many moles are in there, right? We need to know the moles of acid. Because then we could use an equation. The molarity is equal to the moles of H2SO4 divided by the liters of the solution. So we're always going to start out with grams to moles to moles to grams. But this time, are we starting with a mass? No, we're starting with a volume, right? So we're starting with milliliters. And are we trying to find the mass of sulfuric acid? No, we're just trying to find the moles of sulfuric acid. So we can knock off that last step. So the volume of sodium hydroxide is 22.87. That's milliliters, right? And the molarity is going to be liters. So one shortcut we can take is, instead of writing milli, write what milli stands for. Milli stands for times 10 to the what? -3. So 22.87 milliliters is 22.87 times 10 to the -3 liters. Is everybody okay with that? I just took the M, and instead of writing that, the abbreviation, I wrote what it represents. So that's sodium hydroxide. And then I'm going to go to moles of sodium hydroxide. And then I'm going to go to moles of sulfuric acid. So I kind of fiddled this and made it into liters, right? Then I'm going to moles and to moles. So bringing the units down so they'll cancel out. And my liters are going to cancel. My moles of sodium hydroxide are going to cancel. How many moles of sodium hydroxide are there for every liter? 0.158, right? That was given to us. So 0.158 moles of sodium hydroxide per liter. And what's the ratio of H2SO4 to NaOH? That comes from the coefficients, right? For one H2SO4, I need 2 NaOHs. For one H2SO4, I need 2 NaOHs. And so then we're going to calculate that. 22.87 EE -3. That's not proper scientific notation. Your calculator doesn't care. Times 0.158 divided by 2. And I'm getting a bunch of digits, which is pretty typical. 180,673 moles of H2SO4. How many significant figures should that answer have? It should have 3, because my molarity only had 3. This one had 4. Mole ratios are exact, so we don't need to think about them. It's important to remember that leading zeros don't count, right? If you find yourself rounding something to what you think is the correct number of significant figures and you end up with 0, you're probably doing it wrong. Okay, it's really easy to do. So we're not going to count the zeros. We're going to count the 1, the 8, and this next 0. When I calculate the molarity using my equation up here, I want to use the unrounded value. Here, my calculator gave me 3 extra digits. I recommend keeping 2. What's 1 more? We'll just keep all of them. So now I have the moles of sulfuric acid. And I need the volume in liters. Well, they gave me the volume in milliliters, right? We could pull that same trick. I'm going to replace the milli with, well, I didn't leave enough room, times 10 to the minus 3 liters. So now I've got that number that's in my calculator, and I'm going to divide by 22 EE negative 3, and that's going to give...
Would it be 20?
Yes, it would. Thank you. I don't know where 22 came from. I must be having some daydream or something. Thank you. It's 20. So let's fix that on the calculator. So 20 EE minus 3. No, I did something wrong. 0.00180,673 divided by 20 EE negative 3. There. 0.0903. And then it goes 365. So that's going to be 0.0903 molar or moles per liter. Any questions? Titration calculations are very, very common. We will be doing them in lab. You'll be doing them for your lab practical, where you need to do them yourself and not have anybody help you do them. If you go on and take Chem 1B, you'll be doing them there. So this is an important skill to learn. Do you see how it's really just stoichiometry? It's grams to moles to moles to grams. But we're not starting with a mass, we're starting with a volume. They're going to give us the concentration of one of these. They're going to give us the volume of the other. They're going to ask for the molarity. So you find the moles of the missing thing, and then you divide that by the volume that they gave you, and you get the molarity. Do not ever, ever use M1V1 equals M2V2. It seems much easier, but it's not going to take into account this 2, right? And so on an exam, when I will make the stoichiometry different than 1-to-1 to catch the people that use M1V1, you'll get the answer wrong. So it's important to do it using stoichiometry. We have to consider the mole ratio, okay?